Okay, this is lecture 4. So now this is the very first lecture after my business trip to Hong Kong. Okay, now let's directly jump into our main system called as MOS. So MOS capacitor, we will talk about this MOS capacitor from now on. So I think that we will spend several hours, lecture hours on this stuff. But today's lecture is just a description about MOS capacitor. So I think that today's lecture is not that difficult. Here we have a MOS capacitor as shown here. As we all know, the name MOS comes from this metal oxide and not silicon, semiconductor. So MOS is metal oxide semiconductor. That is the reason why we call it as MOS. So since nowadays MOS is too widely used, so everybody says that MOS itself is the only way to make a certain kind of transistors. However, MOS is just among various ways to fabricate a transistor. But practically, this is so widely, so dominantly used in worldwide. So we think that this is the dominant form of fabricating MOS transistor. So you know MOS, and you know this C. This C comes from complementary. This means that here we have two different transistor types at same die, so we can fabricate N MOSFET, which is electron dominant device, and P MOSFET, which is hole dominant device. So although the size of this entire structure called as MOSFET is nowadays orders of about 100 nanometer or slightly longer in this direction, and along that direction also we have certain orders of 100 nanometer, so slightly wider than this length scale, but already 100 nanometer or 200 nanometer is really short. So for example, 100 nanometer is corresponding to 0.1 micrometer. So we feel that this is really short. But compared with these two dimensions, our vertical direction, the third direction, shows even shorter dimension. So here the most critical length scale in this vertical direction is of course the thickness of this silicon dioxide layer, and it is just orders of a few nanometer in this case. So in both cases of the real physical thickness or electrically converted one, equivalent one called as EOT, even in this case they are both in the range of nanometer. So nowadays, if you are working with a state-of-the-art device, then you will find that actually the EOT, so maybe you have heard about it, so oxide thickness. However, this E means that equivalent, not for your actual material, actual insulating material, but converted into that of silicon, pure silicon dioxide, and it is around 1 nanometer or reaching below that 1 nanometer. So real physical thickness is a lot thicker than this EOT value, because nowadays we are using high K material. So although its thickness is much thicker than pure oxide, however, we can get equivalent oxide thickness much shorter, like this 1 nanometer. So usually we use hafnium oxide, and its hafnium oxide's relative permittivity is around 22, and oxide case, how large is it? It is about 3.9. So you can find that there is a 5 or 6 times difference between the EOT of permittivity of hafnium oxide and this pure silicon dioxide. So for example, let's say that if you have 5 nanometer thick hafnium oxide layer, however, if we convert it to EOT, equivalent oxide thickness, then it contributes to only about 1 nanometer. So that is the situation. Let me just explain a little bit further about this one. So here we have a silicon dioxide layer. Unfortunately, we cannot directly attach our high-K material, hafnium oxide, onto silicon substrate. So if we have silicon, then unfortunately we have to have anyway one monolayer of silicon dioxide. So silicon dioxide monolayer has around maybe not exactly, but around 0.7 nanometer thick. So this is really unavoidable. After that, you can add hafnium oxide, and its thickness can be controlled by you guys in fabrication line. So quite easily, like 2 nanometer over even thicker. So if you have this kind of, for example, 2 nanometer, maybe it's okay. Your overall value is overall thickness EOT can be maintained below 1 nanometer. But if you say that I have a 5 nanometer thick hafnium oxide layer, then itself already contribute about 1 nanometer thick EOT, and combined with this 0.7 nanometer one, which cannot be avoided in our technology. So overall thickness EOT value can easily exceed 1 nanometer. But point is, so we are now currently living in 2025, and 5 years later or 10 years later, the required value for EOT is unfortunately just 0.9 nanometer, 0.8 nanometer, or something like that. These extremely small value is required for our next generation transistor. But already we are spending 0.7 nanometer for our, how can I say, our offset. So basically we have 0.7 nanometer for the very first layer, our silicon dioxide. Usually this layer is interlayer. And after that, we have a really small margin for our remaining EOT. So scaling EOT is a really difficult problem for all of us to solve that problem. Okay, so it is really difficult to solve this EOT scaling. But anyway, now you understand the state-of-the-art device has EOT or around 1 nanometer, and in its physical thickness, of course, it's much thicker, like 5 nanometer. But please come back to the other two dimensions, your length direction or length dimension, or your width dimension. In both cases, it is still orders of 100 nanometer. So you may feel that this sounds a little bit difficult, because nowadays we always say that we are now living in the era of 3 nanometer node or 2 nanometer node, but unfortunately there is no real 2 nanometer, real 3 nanometer. So usually what we can get from this structure is orders of just 100 nanometer. Okay, so of course if we consider the shortest one, so I would say that if we consider really shortest one assigned to the one single device, then we can say we are around 50 nanometer or slightly longer. But this is the shortest one, so we are in the range of 100 nanometer for other two directions. Okay, so please think about this case. We are now living in 2025, and our fabrication process has been evolved quite much. But let's come back to several decades ago. So several decades ago, the length scale here was not like 0.1 micrometer. At the time, it was orders of 10 micrometer. Of course, with this direction, also we had similar length scale. Okay, it was really okay to generate or fabricate this such kind of a huge structure compared with our state-of-the-art device. However, still in this direction, it was not that much. So of course, it was much thicker, like 20 or 50, even thicker values were used for our silicon dioxide at that time. But it's true that always this oxide thickness is the shortest length scale we can imagine in a given CMOS technology. So control of this oxide thickness is critically important, because as we will see later, if we introduce a certain variation in this thickness, that affects everywhere in our device performance. So it is critically important to make a uniform oxide thickness, and the rule of thumb is always we wanted to have the thinnest oxide layer. If you can make it thin and thin, then we will do it. But unfortunately, it is not possible at that time. So always having this thin oxide is quite important and difficult job. Okay, so I think that today we are talking about MOS system. MOS means that this vertical structure along this direction, so depth direction. So we will only consider this oxide thickness. But later, if we expand our scope to the transistor itself, then we have to consider also length scale and width scale. Then we will see other different length scales. And since this textbook, Tower's book, is first start from the planar MOSFET, so we will assume that here we have a silicon dioxide or silicon substrate, and its thickness is regarded as infinitely thick. So what is the meaning of this infinitely thick? Means that in reality, the wafer, our wafer is more or less 550 micrometer thick or 600 micrometer thick. But we are now talking about this entire wafer thickness. When we say the substrate, usually we are talking about certain doping well. Maybe you have heard about it. In order to make a certain transistor, we need certain range, reason, with sufficiently high doping densities. For example, if you wanted to build N MOSFET, then what you should do is introduce a certain sufficiently high p-type dopant in this case. So simply speaking, although your entire wafer is 600 micrometer thick, but so-called well in this notation is not 100 micrometer thick. It is just a few micrometer thick. Here you introduce a certain p-type dopant, and on the other hand, if you wanted to make a p MOSFET, then you have to introduce the other doping type here. N-type dopant should be introduced, and at the same time, the thickness of this so-called N well is at most just micrometer thick. So are you with me? So if we just draw the scaled version of this structure, actually you cannot see the thickness of these wells. These wells are extremely thin compared with this entire one. So think about 600, and in this 600 you have to recognize just one or two. If you draw it, then how does it look like? If this is 600, then maybe you will have a very, very narrow region for your doping concentration. So, and well, so simply speaking, we are using just the surface of our entire silicon wafer. Then maybe you can ask me this question. Oh, then are we wasting the wafer? Are we wasting the silicon? Yes, frankly speaking, yes, but the thickness of a wafer is determined as 600 micrometer, not by its electrical property. If that is so thin, like just for example 1 micrometer, then we cannot handle it. How can you just twist it and lift it up, lift it down, if that is extremely thin? So although 600 micrometer is relatively thick from our point of view, so electrical engineer, but this is comes from the ease of handling, wafer handling. Otherwise, if you make it even thinner, then it is easy to be broken and easy to be warped, like a warpage. So many different, so many unwanted things happen. So that's the reason why we keep this value. Okay, but let's come back. So this thickness is around, not infinitely thick, but this is orders of few micrometer in reality. But in this scale, we believe that micrometer is thick enough, so we can treat it as just infinitely thick case, because you know the length scale here is just nanometer, and even when we consider electron gas or whole gas, which will occur just beneath of this oxide or silicon dioxide layer, its average thickness is just around a few 10 nanometer or few nanometer scale. So therefore, micrometer can be easily regarded as infinitely large. So that was the case of our planar MOSFET, and hopefully in this semester, if our lecture goes smoothly as I planned, then later we will talk about a different structure not shown here, another one more relevant to our state-of-the-art device. So in this case, the blue region, so reserved for silicon substrate in this diagram, now it has finite thickness. Even in our simple analysis, this thickness cannot be regarded as infinitely thick. It is because this thickness is just 5 nanometer in reality, or 6, and we are trying to make it like a 4. We are trying, but it's not that easy. So, however, 5 or 6, these numbers are real number we have right now. And please note that previously I told you the physical thickness of this silicon dioxide is about 5 nanometers. So if we just draw it in the scaled version, so then in reality we have this form. Yes, this is silicon, and this is insulating layer and insulating layer, and they have comparable thickness. Of course, here we have very thin layer corresponding to the interlayer, and also here we have a very thin layer corresponding to interlayer. These are pure silicon dioxide, and beyond that point, here we have a relatively thicker insulating layer, and as you know, these are hafnium oxide, high K material. So when you have a look at this system, in this system we cannot treat the infinite thickness, we cannot assume infinite thickness any longer. So we have to consider now finite thickness of a silicon channel region. So we will revisit this issue when we come back to the multi-gate devices. But for a while, just following the textbook presentation, we will start from this planar MOSFET. So it means that your channel length is more or less assumed to be, or your technology node is more or less above 20 nanometer technology node. So Intel introduced their first FinFET technology to this 20 nanometer node. Previously, before 20 nanometer technology, every CMOS was made in planar 1 or SOI 1. So in this case, we can treat the almost the infinite thickness. So I just mentioned that SOI has also a little bit different context. So, but I hope that I can explain it later for our discussion. Okay. So, do you have any question about this MOS system? So, I just told you that although we are talking about MOS system, certainly highly idealized vertical structure, but in this case, the most critical part is oxide layer. Thickness of oxide layer or electrical property of oxide layer is critically important. And nowadays, we are in the range of 1 nanometer in terms of EOT, equivalent oxide thickness, and with the help of our high K material. And later I have told you that for a while the silicon layer or silicon region can be regarded as infinitely thick, but this is not the case for our FinFET technology or nanosheet technology. So in that case, we have to consider the finite thickness of a silicon substrate. That was the summary of this slide. Okay, any question? Okay, okay. So you mean that in this scaled device? So in this scaled device, actually, well, you're right. So in this case, so entire 5 nanometer, 6 nanometer, these are doped with a certain value, because you know 5 over 6 nanometer is not that long distance even in our scaled technology, so you cannot make such kind of a variation in your doping profile. Uniform doping profile is assumed actually, so usually you have a yes. So this is long story, but let me just make it quick. If you wanted to introduce a certain doping, well, usually what we do is a so-called ion implantation. However, if we have such kind of advanced technology, like having silicon layer just to 5 nanometer or 6 nanometer thick, this thickness is not defined by certain other means, but here we do epitaxial growth. So ALD is used. I mean that we spend quite a long time to build silicon germanium layer and silicon layer. On top of it, we also build a silicon germanium layer. And since we are using ALD technology, atomic layer deposition, we can define 5 nanometer or 6 nanometer very accurately. So in this case, during this growth, we intentionally introduce a certain dopant ion here. So we dope here uniformly. After that, this silicon germanium layer can be selectively etched away. I mean that silicon and silicon germanium seems to be quite similar. However, we can find some etchant which have selectivity over silicon and silicon germanium. For example, something can easily remove silicon germanium. However, silicon itself is not damaged by that etchant. So that's the way we define very thin 5 over 6 nanometer thin layer here. So already it is doped when we grow it. So that is the way we make this kind of structure. Okay, so that was a really good question. And also I wanted to say that importance of doping is relatively lower than this planar MOSFET. Previously, so I will talk about it later again and again. In the planar MOSFET case, actually the most important way to control threshold voltage of a certain planar MOSFET device was doping. By controlling doping, you can change threshold voltage. However, in these more advanced technology, state-of-the-art one, since this how can I say, thickness is so thin, so by introducing certain doping, it is difficult to change your threshold voltage sufficiently. Instead of that, we just change the work function of a metal, gate metal shown here. So that is the main knob to change the threshold voltage. So in these advanced nodes, importance of doping is relatively, I mean that also it is still important, but relatively lower than planar MOSFET cases. So the concept of where is no longer valid for this advanced technology. But please note that I have a plan to discuss about the state-of-the-art device more deeply with several lecture hours. So please wait for a while. But before discussing about the state-of-the-art, we have to follow our history, because planar MOSFET is the very basic we have to consider. Without understanding the planar MOSFET, understanding the state-of-the-art device is almost impossible. So please wait for a while. Okay, that was a really good question. And any other question from students? Okay, so please, oh yeah, please. Yes. Yes, that is also good question. So how can you introduce different work function in a same lot? That is critically important question. So the way we do is actually using one type of metal. However, changing certain process condition, it is known that we can change the crystallinity of gate work function. How can I say? Here we have a metal, and by changing process condition, so we can change the degree of crystalline in this surface area. So by changing this thickness, it is known that actually work function can be controlled. So if we introduce, for example, thicker layer or shorter layer, then we can control work function, and the desired work function range is given. For example, from 4.0 eV, this is more close to the N MOSFET application, and if we go to 5.0 eV, then this is more suitable for P MOSFET application. And by controlling the fabrication process, we can actually control the work function between these values. This is the way we control the work function. So I mean that, so although I just told you that this is good for N MOSFET, this is good for P MOSFET, but even when we consider a type of or a given type of transistor, N MOSFET, but sometimes we wanted to introduce different threshold voltages. For example, certain technology provide 5 different values of threshold voltage in a same lot. So as a designer, you can select, I like this standard transistor, or I want to use this low power transistor, or I love to use this ultra low power transistor. What is the difference between them? So if we go to low power version of these transistors, then actually in the case of N MOSFET, threshold voltage increase. So since the threshold voltage increase, so at given zero gate voltage, you have a lower leakage current. So therefore, you have a standard one, low power, ultra low power. So this is just 3 different versions, but in between we introduced many others in it. So yes, so controlling threshold voltage or providing providing many options to our design circuit designers, that is critically important, and nowadays that capability is more or less done by metal work function engineering. That is critically important. Really good question. And okay, but our textbook do not talk about right now talk about this kind of a new thing, because first of all we started from this planar MOSFET. Planar MOSFET case, usually metal is just given. We do not try to change metal work function, and usually the former technique was just to introduce different doping levels for different transistors. Then if you wanted to have, for example, in the case of N MOSFET, if you wanted to have a higher threshold voltage, then introduce more dopants in it, then you can increase threshold voltage. If you wanted to have lower threshold voltage, just to reduce the number of implantation dose is lowered, then you can have a lower threshold voltage, so higher performance. So that was a previous trick, and we will follow the previous recipe. But of course, we will discuss the state-of-the-art devices later in this semester, hopefully. So if everything goes well. Really good questions from our students. So any other? So please interrupt me whenever you have questions. So I love to answer your question. Okay, so now let's go to the energy band diagram. If this is the very first course for semiconductor physics, then I have to say what is the meaning of a vacuum level, conduction band minimum, and valence band maximum. But I will assume that all of you guys understand the basic concept. So I will just dive into energy band diagram. But drawing this energy band diagram is really important. As a semiconductor device engineer, this is the key ability you have to do. So now here we have 3 different parts in our MOS system. Of course, this is metal, and here we have oxide, and this is semiconductor, but in this case silicon. So here we have an example of aluminum. So aluminum has the work function of 4.1 electron volt. However, this nowadays aluminum is not used any longer. So we have a different metal, but this is just shown as a representative value. So here we have a 4.1 eV. So what is the meaning of this work function? So metal work function phi m is that if we have additional 4.1 eV energy to our electron in metal, then we can make it free from this metal system. So now think about this one. I'm walking around and I am bounded the system called as us. So although I can jump a little bit, getting higher and go down, but anyway, it is true that I am bounded to the Earth system. But if I am extremely rich, and if I can take the spacecraft and give them let's go, then maybe I can for a while just to escape from this Earth system and hanging around the space. Of course, I have to come back, otherwise I will die eventually. So now let's think about this system. Here we have many electrons are staying in this range. These are electrons are most important for our electrical interaction. Of course, we have tons of electrons here. So many electrons are here. However, having this energy scale is too difficult, so usually they are not very active for our interaction. So these guys are most active one, and if we provide the additional energy 4.1 electron volt, then this electron can jump into this level, so-called vacuum level, and in this vacuum level, then it is no longer bounded to this metal system. So think about this one. What does it mean when we say that free from metal system? If we have a metal chunk, yes, for example, gold, aluminum, and there are so many electrons, but those electrons cannot move outside this metal chunk. However, if our electrons become a free electron, free from metal crystal structure, then it can easily escape from that metal system. Of course, electrons are so fast, so we can easily find out the electron escaping from this one, this metal. So say that this is just a centimeter away, then we can detect our electron using our electron detector. If we put it here, so simply speaking, this is a vacuum electron, and this vacuum level means that our electrons are no longer bounded to this crystal structure of our metal. Same can happen to our silicon. Here we have a silicon, and however, in this case, discussion becomes a little bit more complicated, because in the case of metal, there is one single level which is important for our case. This was Fermi level. In the case of a Fermi level, here up to this point, electrons are fully filled, and beyond this level, there is no electron at all. So this was only important energy level. However, in this silicon case, we have to consider three different levels: EC, conduction band minimum energy, and EV, valence band maximum energy, and also EF, Fermi level. Oh, here we have Fermi level, and here we have a Fermi level. But in the case of a metal, more or less, the energetic distance between vacuum level and Fermi level is given. For example, 4.1 eV. But in the case of a silicon, as we all know, it really the position of EF taken from this vacuum level is really depends on what? Depends on the doping level. Let's just try to remind you. So yourself, if you have a highly doped anti-Brism, then where is expected value, or where is the expected position of your Fermi level? If you have a highly doped anti-Brism, then your Fermi level will be quite close to the EC value. And if you have high p-type dopant, listen, then your Fermi level will be quite close to EV, valence band maximum. So you know it. So if you don't have any other impurity in it, then maybe there will be a certain close to the mid-gap level, and this energy level is called as intrinsic Fermi level. So this is the Fermi level when your material, silicon material, do not have any external impurity. So this is uniquely defined. So EI, intrinsic Fermi level, can be uniquely defined. However, EF, it really depends on your doping condition. So by changing doping, you can change it. So therefore, of course, for silicon, we can define also work function. However, if we define work function as just a difference between vacuum level and Fermi level, then depending on the doping concentration, this work function can differ. So, good. We wanted to have more doping independent quantity. So more unique quantity is required. So instead of this work function, in the case of silicon or any other semiconductor material, we prefer to consider this concept. So here we have chi, and this is electron affinity. So this quantity is just difference between vacuum level and conduction band minimum level. So simply speaking, E vacuum minus EC. This is corresponding to this Q chi and whatever. So really, I don't think that there is a globally, universally adopted notation for electron affinity. So you can use whatever you like. So I just follow the notation by Professor Tower. So here you can see the energy difference is expressed as this electron affinity. So if we write down in this case, there is one thing. If you write down in this case, what is the dimension of this chi? Is this EV? No. In this case, if we have this Q is corresponding to Coulomb scale. So in this case, we have just volt. Okay. So if you write down instead of this one, for example, if you write down in this way, yes, this is just the EV quantity, energy quantity. However, if you add this one takes the Coulomb part, so this one has just a unit of volt. Sometimes people say EV and volt interchangeably. So also I will do so mistakenly, but I will try to avoid this kind of habit as much as possible. So please follow me. You should distinguish two different quantities. One is EV, this is energy, and volt, this is volt. Of course, by multiplying the elementary charge Q, we can easily convert it from volt to EV, but this is not good to be confused by these two differences. So anyway, electron affinity is given as 4.05 EV. So it means that although you change your doping concentration, your electron affinity for silicon will be always 4.05. Although work function can change drastically between this value to that value quite much. Well, anyway, now just to consider this example. Here we have 4.1 EV as a metal work function of aluminum metal, and here we have highly doped p-type resin. So please try to estimate the work function inside this silicon material, then how large is it? Of course, here we have affinity, and in addition to this affinity, we have to consider the energetic difference between EC and Fermi level. And if we have a high p-type doping, then maybe this EF will be quite close to valence band maximum. So please remember that this band gap EC minus EV of silicon is about 1.12 EV. So you will find that actually if this is the case, then our Fermi level seen from this vacuum level is about 5 EV or even higher. Okay, so in this case, we are now just talking about 3 separated material system: metal, silicon, and in between we have oxide. So they are separated. However, as we always do in our textbook, then the next step is just to attach them together and make this just combine the system. Then the rule of this attachment is quite simple. Fermi level should be aligned. This is the rule. So Fermi level, when the Fermi level is aligned, so of course here we have a silicon dioxide layer, but for a while just forget about it. And here we have EF. This is taken as 0, and also EF that is taken as 0, and they should be aligned. Why we have to have this aligned values? So if that is not aligned, then we will have current conduction in general case. Of course, in this case, here we have silicon dioxide. It prevents the transport of electrons. But in general, if we have the connected system, then they share the same Fermi level. So now we have Fermi level given value as 0. Then please try to the position of your vacuum level in both cases. What is the value of your vacuum level energy in this metal part? Of course, your energy will be 4.1 EV because Fermi level is taken as the reference value 0 electron volts. So are you with me? So this is not that difficult because previously we know that the difference was 4.1, and if this lower one is 0, then of course the upper one will be 4.1. If I say that this is 1 EV, then what will happen? If this is 1 EV, then of course that will be 3.1 EV. That's so simple math. So in this case, since we are using Fermi level as the reference energy, 0 electron volts, so we will have 4.1. Let's try to the same thing for our silicon case. Even in silicon case, we will use Fermi level as the reference value. Then where we can find the vacuum level, as we discussed up to now, vacuum level would be around 5 electron volts. This 5 volts is not a definite number, so of course depending on your doping concentration, it can highly change. However, since we are talking about highly doped p-type resin, well, values will be around 5 EV. So it means that when we attach it together, attach two materials together, then although Fermi level is aligned, but if we consider the vacuum level of these two materials, they are not aligned at all. Here and here we have a certain difference. So what does it mean? It means that we have a certain electric field between them. So that is the conclusion. So means that when we, so I hope that already all of you already attended the basic course for semiconductor physics. That happens also in p-n junction. If you have the same material called as silicon, but they are doped differently, and when we merge them together, then although they are belonging to the same material system, we can have the built-in potential and built-in electric field in it. Quite similarly, now we have two different systems called as a metal and a semiconductor, silicon. When they are attached together, also we can expect a certain built-in electric field. So this is the case. However, the difference is when we merge p-type silicon and n-type silicon, so usually we expect that they are directly attached. However, in this case, please remember the existence of what? Here we have something called as silicon dioxide. So that introduces quite much difference. Since silicon dioxide layer is existing, even though, I mean that, please, from now on, that is really important. So let me just state slowly. Since we have a perfectly insulating layer called as silicon dioxide, even in the case where our two Fermi levels are different, even in the case that there is no current conduction at all. I mean that up to now, yes, in this case, when we have aligned Fermi level, since the Fermi level is aligned, so there is no current conduction at all. Everybody can understand. However, let's say that if this is your Fermi level, then what will happen? Here we have Fermi level, and here we have Fermi level. If, for example, let's say that this is -1 eV, then there is a Fermi level difference. And if that happens in your p-n junction, what happens? If you apply 1 volt to your p-type region, anode region, then you will have a lot of current conduction, because this kind of Fermi level difference should be eliminated. So our device is actively providing our charge carriers into this p-n junction system in order to eliminate this Fermi level difference. However, in this MOS system, due to the existence of silicon dioxide, even though we have energy difference, Fermi level difference, there is no current conduction. So are you with me? Previously, if we have just silicon, then maybe there would be high current conduction, but it's not the case. So now that's the reason why we can go into the next part. Since in this MOS system no current conduction is applied, so we can still treat each part separately. So it means that if we apply different gate voltage, then we can only change the Fermi level of our metal part selectively. So let me just repeat once again. So now here we have just 0 volt case, and when we apply gate voltage equal to 1 volt, then what will happen? Here we have metal, silicon dioxide, and silicon, and by applying this 1 volt to the metal part, only Fermi level of this metal part is downward shifted by amount of just 1 electron volt. So now new Fermi level becomes just -1 eV instead of a previous 0 volt. It does not make any impact on this part in terms of carrier transport. Why? Because here we have silicon dioxide. So silicon dioxide completely isolate these two parts in terms of carrier conduction. Anyhow, they cannot send one electron from here to there or send one electron here to there. The communication or exchange of electron is not allowed between them. So we can safely change only Fermi level in the metal part. So if we go to that way, then now by changing the gate voltage, we can change this EF. So previously, that is the reference value. When you apply 0 volt, then that was the value of your Fermi level. How can you make this diagram? If you wanted to place your Fermi level in this position, upward position, then you have to apply a negative VG value. Okay, because this is electron picture, not whole picture. So when you apply -1 volt, then this is multiplied with our -q also. Therefore, it yield +1 electron volt upward. So this is direction for our negative gate voltage. And if we apply positive gate voltage, then there will be negative or downward shift of our Fermi level. Okay, so now let's play with this metal part only. By changing the gate voltage, you can control the position of your Fermi energy. And by changing it, happen to be you can find a condition where your vacuum level in metal part and your vacuum level at silicon part are aligned together. So of course this is just happen to be the same. Let me just give you one simple example. Previously, let's say that there was a 5.0 EV in our case. Then how can we match these two vacuum levels? By applying your gate voltage equal to -0.9 volt, you can align them. So are you with me? If we had previous the work function difference, for example, 4 electron volt and 5 electron volt, that difference should be compensated by our additional gate voltage. So usually, if we have this kind of configuration, the metal work function quite close to 4.0 eV, and silicon work function quite close to 5 electron volt, then usually the bias condition to match the conduction band level, so vacuum level is about this number, and this condition is called as flat band voltage. Simply speaking, if you apply flat band voltage to your gate, then your vacuum level profile becomes really flat. That is the case. Why this flat band is so important? So when we have a flat band, now even in this silicon part, we just have no electric field at all. So therefore, what we can expect is everything, since there is no electric field, it means that no electric field and no change in electric field, it means that everything is its neutral case. So we can think that the system is in its can say homogeneous case. So let me just case flat band voltage. When gate voltage equal to the flat band case, what we can have is here we have a completely flat vacuum level. So although their Fermi levels are different here and there, of course in general case, if we have difference in Fermi level, then there will be the transport of electrons. But as I told you several times, due to the existence of silicon dioxide, even though we have different energy Fermi levels, but there cannot be electron transport. It's like very similarly, we can think about this case. This is a water tank, and there is in between, there is a certain barrier. And let's say that here we have high height and relatively low height. However, if we maintain this barrier between them, then there is no change in its water level. However, if we just remove it, then what will happen? Quite quickly, so they will be just this difference will be diminished, and we will have a globally balanced level, water level. So please make an analogy between these electron case. In the case of our electronic system, this point, this Fermi level can be regarded as the highest level of electron occupancy, and also here we have a highest level of electron occupancy. So in general, if we have a difference of these two, then highly energetic electrons in the left part will move into the right part. However, silicon dioxide just prevent just such kind of a transport. So that's the reason why in this case we can maintain this Fermi level difference. Instead the Fermi level is maintained, but here we don't have any gradient of our vacuum level. So this is flat. And if I ask you what is the electric field at this point, then electric field is just given as gradient of this vacuum level. So please try to calculate it. That will be just 0. So are you with me? In general, we have to have this kind of notation. So electric field is given as minus Q. This is what happens? So sorry about that. I just messed up. So electric field is given by this form. So electrostatic potential, take its gradient and multiply minus sign. This is the expression for electric field, and now we have just a flat band. So taking the gradient will give us just a vanishing value. So we have no electric field at all. Then also we can ask this question. Then what is the hole density and what is electron density at this point? Can you guess? Yes, you can. If you know the energetic difference between your Fermi level and EC and Fermi level and EV, you can immediately calculate the hole density and electron density. What you can get is, okay, you have a negligibly small electron here, and you will have quite a high hole here, and of course also you can say that the product between electron density and hole density will be just given as square of your intrinsic carrier density. Then of course this P density would be quite close to your acceptor density, so you will have Ni square divided by your anode, acceptor density. That will be the situation, and everywhere inside in this silicon part, you will have that solution. So flat band case gives us just a uniform solution. Everywhere inside the silicon, the hole density is given as acceptor density, and electron density is given as minority carrier density corresponding to the p-type Na case, and there is no electric field. So it is really good starting point for our next calculation. So please, let me just come back to 0 volt case. In the case of gate voltage equal to 0, in this case, our system has internal electric field from its beginning. So it is difficult to consider, do certain analysis. But if we have this flat band condition, then our starting point is just uniform semiconductor material. Semiconductor material is in its, in its neutral case. Only doping determines its properties. No other effect from the existence of attached silicon dioxide and metal. Their effect can be neglected at this special case of flat band. That's the reason why we start from flat band condition. Now, if we additionally apply certain voltage over flat band, then we just treat it as a special excitation. For example, let's say that flat band voltage happen to be minus 0.9 volt, let's say. Then in our current view, when we apply 0 volt to our case, this is treated as okay, starting from minus 0.9 volt flat band condition, we additionally applied 0.9 volt. So although this number itself is 0, but its a hidden balancing point is not 0 but minus 0.5. If we can find flat band condition, then our analysis can be greatly simplified. So simply speaking, if we have this condition, so even though when we apply 0 volt, our MOS system is already driven toward this positive direction. What is the positive direction here? Positive direction means that metal is positively driven. So flat band condition, we have this flat vacuum levels, and now let's say metal is driven by amount of 0.9 volt. So what will happen? In this case, we will now drive our band, metal part band, amount of 0.9 EV downward here. So it means that now, if we consider this is flat band condition, and now we will have this 0 volt condition, and there will be, we don't know exactly what happens in between, but what we can say is, okay, these two values are two boundary conditions, and we will have eventually this kind of curvature in our vacuum level energy. That is the simple idea we can have. So please note that flat band condition is quite important because it makes our analysis easy. So as a criterion for our analysis, if we apply the gate voltage higher than flat band condition, then our metal part is now driven downward. think about the other way around. For example, flat band condition is minus 0.9 volt happen to be, but you apply gate voltage equal to minus 1.9 volt. If you apply in this case, then your metal energy is no longer going downward, so it goes to upward. You will have an energy band diagram having this kind of curvature. However, in real application, you usually do not apply negative gate voltage to your device. So that's the reason why in many cases we just consider this kind of energy band diagram. But in principle, flat band condition can be regarded as the criterion where our band diagram goes upward or downward in our metal part. Okay, so now let's go to. So this slide just to repeat my explanation. So now, even though we apply gate voltage equal to 0, but band is no longer flat, but now we have to have a downward bending due to the difference between our gate voltage and flat band voltage. So now we can expect this kind of behavior. But please note that here it's not correct at all. So you should be able to understand or recognize the problem of this diagram. Where do we have an error or mistakes in drawing shown here? Energy band diagram. So for example, do we have any mistakes in this part, that part, or this part, that part? Here, please pick one point. What is the main problem of this diagram? This diagram has problem here. Please have a look at this one. Let me just draw in magnified view. If we just believe this diagram, then this is silicon dioxide and silicon, and it says that in silicon, what is your electric field? Yes, electric field equal to 0 because energy is just flat. And how about this? In this case, electric field is not 0 at all because this is related to just a gradient of your potential energy. So simply speaking, if we just believe this one, then here we have discontinuity of our electric field. At interface, can you allow discontinuity of electric field? It's not. The only way we can allow that discontinuity is if we assume the existence of a surface charge, the charge having 0 thickness, then we can assume the discontinuity. However, right now, our length scale is quite small, like just a few nanometer. This is just a few nanometer, so there is no such kind of surface charge at all in this case. For let's assume this way. So this discontinuity is not allowed in. So then what we can expect is this part here should be changed. Then who can change it? Let me just explain. Also, let me allow just 1 minute. Here we have two different material, and we know that this is long. So okay, I understand. So in order to solve this problem, so the silicon dioxide will yield. So inside this silicon dioxide, I will just make the interface electric field equal to 0. can you expect this kind of situation? Once you say that inside the silicon dioxide interface field equal to 0, then it means that all over your silicon dioxide, the electric field should be 0. So inside this oxide layer, you have no way to change the electric field in this one-dimensional system. So simply speaking, this one, oxide case, oxide region cannot yield at all. Then what is the other possibility? Yes, now silicon part will allow electric field inside it. So this electric field sent from this silicon dioxide part will be the main cause of inversion phenomena. So we will talk about it in later session, Wednesday. Okay. Thank you for your attention. And if you have a question, then please come to me after this session is over. Thank you.